ABB brings you the ACH580 variable frequency drive with sensorless pump control. What is sensorless pump control? Sensorless pump control allows the pump motor drive combination to continuously identify head pressure at any point in time, optimizing the pump speed in order to achieve a more energy efficient pumping and give you accurate pressure control without the need of external feedback signals. Sensorless pump control is standard on the ACH580 and the ACQ580 drives family. Sensorless pump control is simple to set up for individual motor pump combinations. Only 10 data points relating head pressure to flow to power are needed. The drive uses the relationship of power to flow and flow to head pressure to calculate the required pump speed needed for the head pressure at the pump, allowing the pumping requirements to be met without the use of an external feedback pressure sensor. With the elimination of external pressure sensors and associated wiring, overall installation time and costs are reduced. The drive is the controller of the system, reducing the need for expensive external hardware, saving you money. Sensorless pump control also works in conjunction with other drive pump protection features like high or low pressure flow protection, pipe rupturing, closed valve or blockage, pump cavitation. Sensorless pump control is one of the many innovative solutions brought to you by ABB and the ACH580 drives family. Now let's take a look at what it takes to set up sensorless control. Sensorless pump control requires pressure and flow. We have a magnetic flow meter, we have an output pressure meter here, we have our pump with our motor combination. So we are going to do the testing of the pump and motor combination. Simply taking some pump charts and trying to figure all this out won't be accurate enough to have accurate sensorless pumping flow. In this case here, we're going to have a limited range of what this pump will actually run at. It's actually a 2 horsepower motor, but I can only get about a half horsepower of total loading on this system. But for what we're going to do, this will work out just fine. We got our drive, and we got our throttling valve. This throttling valve, from fully open to fully closed, will help me collect my data points. Now, to start this out with, we need to find out the pumping characteristics of this pump and this motor. We need to know shaft horsepower, system flow, and system pressure. In this case here, I have it set up for system pressure in feet. I have system flow in gallons per minute and shaft horsepower in horsepower. On my keypad, I've set it up so line 1 is shaft horsepower, line 2 is feet of water column, and line 3 is flow, gallons per minute. I'm going to start the drive up. We got the drive going, and let it stabilize. When you're doing your test in your testing facility, you will need to let the system stabilize. It may have to run for quite a while. In this case here, we're very limited in time, so we'll continue on. I look at this right now, I see that my horsepower is at a 0.56 horsepower. I see that my water column right now is 19.59. And I can see that my flow is 38.46. It's stabilized at those points, and this is my fully operational point. If I go all the way to the other side and stop the flow, that's my zero flow pressure, my zero flow right there. Okay, that's one data point. So no matter what, we have one data point. And at the top data point, the 10th data point, that's going to be 38.46 for flow, gallons per minute. So what we need to do is take like 38 gallons per minute, divide it by 9. That gives our first data point of 4.22. That would be data point 2. So let's start our system out. Let's get our data points. I'm going to go down to a closed valve scenario. That's data point 1. I'm going to use the left and right key and the up arrow to do a screenshot to save the data from the screen, and we'll do some magic editing and show it right here. Now, the next data point is 4.22. So I open the valve up until I get a flow of 4.22. When I get my flow around 4.22, remember, you don't need your data points to be perfectly accurate. You just wanted to break them up so you have 10 data points. I get that flow ration around 4.22. let it stabilize. At that point, I do another screenshot. I continue on. Next point is 8. So I go up to round 8. Get to round 8, let it stabilize, and we'll do another screenshot. And we continue on like this. Since we've got 2.22, we'll go to 13. At 13, screenshot. We'll continue on. 17. There's my 17 screenshot. Let's go on to 21. There's my 21 area there. I'll do another screenshot. We're going to go up to 25. There's 25. We're going to continue on to 30. There's my 30 area. Move on to 34. Oop, a little too high. There's 34. And then we go fully open. And this is our last data point, the 10th data point. Now, you could do this with 5 data points. You do need to have the first data point at 0 gallons per minute. Okay, so 0 flow. If you do it with 5 data points, the system won't be as accurate as 10 data points. So you got between 5 and 10 data points you can enter into the drive. We're going to go through some of the rules, and we're going to look into how we handle this data next. We're going to look at it in Excel. I'm going to take the information that I just got, enter it in Excel, and show you a graph. So let's move on to that point there. In this Excel sheet, we have a simple chart set up for shaft horsepower, system pressure in feet of water column, and system flow in gallons per minute. Looking at this chart, what we're going to do is we're going to fill out the chart, and we're going to look at our graphs for head to flow and our graphs of power to flow. Let's take a look at the information that we have. The first information for point 1 was at 0 flow, so let's enter it into the chart. The next information that we have is for data point 2. Then we have data point 3. And as we enter this information individually, we're going to start building up our graphs. We want to do this to make sure that we have a good system for sensorless pumping. Depending on the pump and motor combination, we need to have data points that allow the drive to do the calculations. So here we are. We've entered our data points in, and for our head to flow, with pressure in feet of a water column up in the vertical and flow in the horizontal in gallons per minute, we can see a nice arcing curve that allows the drive to do calculations for head to flow calculations. When we look at the power, which is the power of the horsepower of the shaft of the motor, to the flow through the pump, we can see that we have a slope here. This slope allows the calculations for power to flow to be completed. This is all good information. This shows that this pump and motor combination will work for sensorless flow. We have some rules that we have to follow, and one of the rules is the power rule. Power 1 must be less than power 2, less than power 3, less than power 4. If you look at that, power in data point 1 is 0.31 horsepower. Power in data point 2 is 0.33, and power in data point 3 is 0.35. As we go through all our 10 points, we follow this rule. That's good news. But pressure, we have what they call a liable pump right now. What happens is pressure number 1 to pressure number 2. Pressure number 1 must be greater than number 2, which must be greater than number 3, which must be greater than number 4. But when we look at it, the pressure at point 1 is 39.02, but the pressure at point 2 is 39.11. And then at point 3, it happens to fall back down to 39.02. What's happening is, and so we don't normally run at that point, and so it's not a problem. What we do is we basically put a number, we take care of this issue right here by putting a number in place. And I'm looking at 39.02, then 39.11. So I'm just going to go to 39.20 and enter that as my data point. Now I follow the rules. So this will be the data that we enter into the drive. We have multiple ways of entering into the drive, and we'll go through those in a moment. Now that we have our data and we've evaluated it, we need to look at how to enter the data into the drive. The first time we're going to look at is using a keypad emulator to put the data into the drive. It's going to simulate the keypad. I'll show it right here. We're going to use this keypad simulator to take a look at the ACH580's keypad and how to enter the data in for senseless pumping. The first thing we do need to do, right now it's set up, let's just look at the keypad's display right now. The drive is off. I go into hand mode. The drive is going to accelerate up to 60 hertz. 60 hertz is my current speed reference. I can change that by going up and down arrows right now if I wanted to. The drive gets up to full speed. We can see our water column pressures, 38 feet. Shaft power and horsepower is 0.367, and gallons per minute is about 9.35. So I can stop this, and let's start some programming. I did step some programming for the display, and I got the motor programmed all done. But let's look at putting in our data. So we'll go to menu. We're going to need to go to parameters, because we want to do senseless pumping. So we'll go into parameters, and we'll look at the complete list. And the first group we're going to go to is our senseless settings. Group 81. We're going to go in Group 81 to set our units up. These are the units that are going to be used for senseless pumping, and I want to set them to US units. Okay, I can back up and I can go to Group 80 now. Alright, I come up in Group 80. I select Group 80. In Group 80, we have multiple different parameters here. If you look at it closely though, there's no parameters in Group 80 that will support entering in our chart data. That's because we need to set it up for senseless pumping. And that means we're going to need to go to 80.13 flow feedback function. If I go into edit here, here's my options for flow feedback function in Group 80.13. And if you look down, you see we have option 100 here is HQ curves. That's head to flow curve. And there's PQ curve, that's power to flow curve. And then there's power to flow and flow to head curves. That's our senseless pumping section. So I save that. Once that happened, a whole new set of parameters have now opened up in Group 80. And if I go down here, here's our curves. H1 curve through H10. Then we got P1 in horsepower through P10. And they say horsepower because I converted that to horsepower earlier. Then Q1 all the way up to Q10 in gallons per minute. And that's because we went into Group 81 and put gallons per minute in. So at this point, what we'll need to do is we'll need to enter in our data, starting with H1. So I'll just enter in a little bit of data real quick, and then we'll jump ahead real fast and with the data entered. But editing is real simple. You can go in, you can edit it. Our first number for H1 is 39.2. Save. There's 39.2. And I can go down to P1, which was 31.31. P1 edit was a 0.31 horsepower. So it's 1. Save that. And Q1, the original Q1 that we had, Q1 is 0 gallons per minute. So there's nothing we have to change there because that was 0 gallons per minute. Save. And then we can go back up and we can continue entering data in. So we'll skip ahead with all the data entered in. Now that we've entered in all of our data, we have all of our flow data is entered in Group 80. On top, it will show 8001 is our actual flow calculations, actual flow percentage, total volume that gets built up over time. Here's our estimate pump head is. That's 8005. That's very important. We need 8005 because that is, when the drive is running, the estimated pump head that is being calculated. If I was to start the drive up right now, it's showing estimated pump head as the drive speeds up to 60 hertz. And at 60 hertz, my estimated pump head is 38.57 feet. 60 hertz, 38.57 feet. That's my estimated pump head at this time at 60 hertz. So I can stop it. Now what we need to do is we need to take a look at what we can do with this drive and how to set up the feedback. Therefore, we're doing feedback and everything based on frequency. So let's set up our frequency chain. So group 28. Go to edit, and right now my frequency is set to A analog input 1 scaled, and that's not what we want. We want to set this to our PID loop. We're going to go down to frequency reference 1, edit, and we're going to set this to PID. And this will be our first PID loop. Right there, save. We back up. Next thing we go to is group 40, because group 40 is our PID loop. There's your PID loop. Select. So let's start out with our PID loop in group 40. The first parameters we need to go to is going to be 4007. 07 is our operation mode, and currently it's off. So we're going to enter that. We want it to be on. We can just go it's on all the time, or we can go when it's on when running. In this case, we'll put it on whenever the drive is running. So whenever the drive is running, the PID loop is on. We need to know what the PID loop needs to look at in order for it to operate. So let's just go down to the next parameter, which is 40.08. And that's your feedback source. Right now it's an analog input 1 scaled. We don't want that. We want to have it set up to, until we group 80, we go to other, we go edit, and now we go to group 80. And there's 80. That's our flow calculations. That's group 80. So we select group 80. And 8005 is our estimated pump head. So this is our calculated pump head. And this is what we want to aim for in our PID loop right now. So we'll save that. So right now our new feedback source is estimated pump head. I'm also going to put my set point in. Right now I need to set a set point. My set point is going to be, it's going to be 4021. There's my internal set point. Right now it's at 75 degrees Fahrenheit. And we're not working that way. We need feet of water column. So we'll set this to 20. We'll get that done first, and we'll take care of our units later. Save. That's our internal set point. We need to look at our feedback, how we're going to bring our feedback in our system. And that is 31. We are not going to be inverted. So we're going to have our feedback directly from 8005. So it's going to be not inverted. Save. And I'm going to need to add a little bit of gain to my system. Actually, a little bit less because of my system the way it is and the size of it. So we are going to put it at 0.3, save. And our integration time is only going to be 1 second because of our fast response time that we have on this small unit. All right, let's get our units fixed here. We're still looking at Fahrenheit, so we get down to 79 down here. There's my units right there. I'm going to edit that. And my units are in Fahrenheit. We want to get these units to feet of water column. Inches of water column, just pass that up. Feet of water column, right there, last one. So we can save that. Now when I look at our units on the system, go back to the top, group 40. And there we are. Group 40, feet of water column. So right now, the system is set to do 20 feet of water column in auto mode. If I go back to auto mode now, you see 20 feet of water column is showing up. That's our set point right now. And the drive is coming up to speed to get up to that 20 feet of water column. And I can back up and we can look at our display. Here's our motor shaft power. Here's our system pressure in feet of water column. Here's our gallons per minute. The drive's still ramping up. There we are. We have our restriction valve is kind of closed. We're only doing about 6.8 gallons per minute. We got 20 feet of water column. And I'm going to go change that valve right now. So as I change my valve, I've changed the throttling valve. Get the system going at a much faster speed. And we see here is the system's getting itself up to a little bit over 20 feet of water column. It's starting to stabilize. I can look at the next screen over that I had set up. And there we are. Output frequency 58 hertz. System pressure is about 21 feet of water column. If I back up, it's at 21 feet of water column. 35 gallons per minute. And we're set to 20 feet of water column. Let's say I want to change this. And I want to bring it down to, let's bring it down to 18 feet of water column. Now that is actually a parameter that we need to go into because that is what we're setting up. And that is your PID set point. There's your set point. You can go to edit. If I want to change this, I can change it down to 15 feet of water column. There's 15 feet of water column. I save it. My new number up there is 15 feet of water column. My drive is now changing its speed to work down the 15 feet of water column. Now that we have our data in the drive, let's use Drive Composer to take a look at the data in the drive and the different functions in the drive. We also can graph it and see a few more data points as we change our different positions on the valve. So we're going to use Drive Composer now and do a short little video on Drive Composer. All right, looking in Drive Composer, let's look at some of the parameters and how they affect each other. Up here I'm looking at parameters. I'm going to lower down our graphing right now. And one of our main groups is the PID set point, set 1. So the PID process set 1, group 40, is where I've set up my PID loop. And the PID loop I have set to on when the drive is running is set 1 feedback 1 source is parameter 80.05. So that's parameter 80.05. Let's slide down to parameter 80.05 so I can show you what that is. Parameter 80.05 is the estimated pump head being done in the flow calculation section. So back up to the PID loop area. What we have here for this system, I actually set my feedback filter time to a 0.3 off of the standards. My source is my internal set point. Right now my set point is set to 15 feet of water column. I can move that to 18 right now. So I'll make it 18 feet of water column. Enter. My deviation inversion is not inverted. My gang is a 0.3, and my integration time is 1. These were all set up to allow the system to be stable for this system that I'm using. And my units are feet of water column right here. Let's go down to group 80, flow calculations. Here's the flow calculations. What's happening here is I've set the P to Q, which is power to flow, and the Q to H, flow to head, curves. That's my feedback function. This had to be set up to set our data up as I showed earlier. And here's our data that we entered in, and your feet of pressure, your horsepower, and your gallons per minute. And so that's your H, P, and Q data. The other thing that I put in here is I've got my flow units as gallons per minute. I got my length in feet. One other thing I'm looking at when I look at my settings in here, so my chart down here, is I have the analog input set up, so AI1. I've set up AI1, which is a 420 milliamp input, and I have it set up as a scaled input. So right here is my AI1 scaled. This is what the meter's reading. Right now, statically, the meter's reading 0.052. When I look at the meter, it's saying 0.007. So it's a decimal pointer. It's a slight bit off, not enough that will make any difference. Because I'm saying my input milliamp value is 4.02 milliamps, not 4.0 milliamps. So it's a tad bit off. Not enough to make a difference for what we're doing here. So I'm going to start the drive. I'm going to put it in auto mode, and that's going to start the drive. And what I'm doing is I'm going to turn around. I'm going to turn on and start the graphing right here. So what's happening is I've started the drive already, and the drive right now in red, that's the speed of the drive's output, and it's bringing up the speed right now. And in green and orange here, we are looking at our PID feedback actual and our AI1 scaled. So our A1 scaled, this is what my meter's reading, my pressure meter's reading, and the PI feedback actual is what the drive expects the calculations of the head pressure to be at. And PID set point right here is the set point that I set it to. As you can see, I've set it to 18-foot water column, and I've got right now 17.6. I'm at 57 hertz and 17.5. When I look at my numbers, here in my PID process section, here's where these numbers are coming from. The output actual is the output frequency that the drive's expected to run at, and here's my set point, and here's what my calculations are right now. And it's stabilizing. It will eventually get itself up to 18, and these numbers will get closer and closer. If I go down to group 80, looking at group 80 right now, because it's doing an actual flow calculation right here. This is based off of its flow calculation from the data we gave it. And it's claiming it's doing about 36.8 gallons per minute. And I'm sitting here looking at the meter, and the meter says 36.34. So this is actually an actual flow calculation that's coming up with. This isn't from the actual meter itself. And it will do total volume and other things. You can adjust this stuff. Let's take a look at what happens when I change the system. I'm going to change my throttling valve and drop my flow down. Okay? So I've dropped my flow down. The whole entire system's starting to change. What you're seeing is now the speed of the drive is slowing down. My pressure ended up being a bit high. It's trying to catch up to my set pressure right now, but my actual pressure on the output and my scaled pressure are relatively very close to each other right now as the drive slows down to a point where these numbers start to line up. And it's claiming theoretically that it's got 7.65 gallons a minute, and by calculation it's a bit off right now. They're only doing about 6-point-something gallons per minute right now. But that's a calculation base there. It's not actual flow. It's what it's calculated at. But it's still starting to stabilize out. I get back down to my PID loop area right here, and when we look at it, it's looking at 41 hertz, and that's 41 hertz there. I'm at 17, 18, and 18. So right off the bat, the system is stabilized at 18 feet of water column. So 18 feet of water column is what we stabilized at. And as I can show you, I can go into the system and I can change my set point. And by changing the set point, I can change the way the system's run. So here's my internal set point. If I change that, let's push it up to 20 feet. So I'll go to 20, enter. At this point, the drive is going to, there's my jump right there in the blue line. The drive is speeding up. It's trying to stabilize out at 20 feet. We're seeing 19 feet here. Here's 20, and it's starting to stabilize out. This is what it looks like in Drive Composer, and here's where we're getting our data from. And as I change the throttling valve, the drive will change speed accordingly, and the system will accelerate, and then it will go work on its way to its calculated values. Right now, it's catching up to that 20 feet of water column that I set it to. It's speeding up. Right now, it's got to speed up to a relatively high speed to catch 20 feet of water column. Pressure is a little bit high right now as it's trying to catch up to the 20 feet. It's still calculating it out. I think I might have just rolled myself too high for this section of the graph. But it's getting close. We're at 19 and it's showing 21 actual on the meter. So they're stabilizing out as they get closer and closer. And when I restrict the system, it changes its characteristics again. So here you are in Drive Composer Pro, looking at your graphs as I change the loading on the system, and how the system works its calculations to determine the head pressure that you want at the output of the pump. And it's doing this through sensorless pump control. This analog input is not connected to anything. My feedback source is parameter 80.5, so 80.05 is the feedback parameter, and that is this parameter right here, estimated pump head, in the flow calculation section. This concludes this video on sensorless pumping for the ACH580 and ACQ580 drives.